Hopefully our beginning magician here pulls downward, as suggested as the hint for you in The Jerk Who Came to Dinner. The cat might have interfered ever so slightly. So how lazy can you be? Not a challenge for you, just what we've entitled the notes here. How lazy can you be? The question A, what is dynamics? Well, let's review kinematics, being the language to describe how something moves. And going into dynamics now, being understanding the cause of motion. Kinematics, the how, the mathematics of how things move. Dynamics, understanding what causes motion, forces involved with motion. And also, things not moving is a form of motion. Together, these two fields of study of physics are called mechanics. Kinematics and dynamics make up the branch of physics we call mechanics. Letter B. How did the ancient Greeks describe the cause of motion? So first of all, the Greeks on this European continent map. Greece is right here. And the greatest country of them all, brilliant, Wales. This is from a former student of mine. In college physics, my life is still ruled by a teacher from the UK, this time Scotland. He is pretty cool, and I just learned that he too has Superman physics problems as demonstrated in the quiz I took. I thought you'd enjoy seeing the problem. Have to thank you for teaching AP Physics my senior year. It's come in useful in my physics or scientists and engineers class. It is mostly review right now. So, the great country of Wales, the United Kingdom altogether. You just can't escape us crazy physicists using Superman. We're going to show you now some motion of a Superman case and just see how it moves. And then you'll see the Greek interpretation of that movement. Greeks stated that a force was required to keep an object in motion. And you can see it looks as though that case does need to have a constant force applied for it to move. Letter C. How did Galileo describe the cause of motion? We looked a little bit at Galileo in Physics A and the relationship of pendulum length with the frequency at which the pendulum swung. And now looking at your European continent again, the country from which Galileo heralds is Italy, right there. And the greatest country of them all. Alright, so Galileo described motion a little bit differently. The Greeks, over here, thought that motion would happen if you kept applying a force. So, scooting that Superman case across the wood table, you had to keep applying a force for it to move. Galileo thought very differently. Galileo pictured a situation where you did not have to consider air resistance or friction. And in this little vision of lawlessness, I like to call it, where there's no law of friction, he imagined that an object would continue in motion once a force had been applied to it, not that a motion was needed to keep the object moving. Greeks felt in order for something to move, you had to keep applying that force. And you can see why they would think that, and you can see why many people today in the 21st century think the same thing. You have to keep pushing on something in order for it to keep moving. Galileo in the 17th century, 1600s, thought quite differently in that if you have an object and you apply a force to it, it will keep on moving. The reason that the object stops is because of friction. So if there weren't friction, he stated you could apply a force and that object would keep on moving if no friction were present. Now, definitely Galileo is held in high regard in the world of physics, and most notably, achievement of high status is when Star Trek mythology names a shuttlecraft after you. So the Galileo shuttlecraft in the original Star Trek series. One small improvement I might recommend. Beautiful. There is an actual Earth-made satellite known as the Galileo Space Probe, and its mission was to go to Jupiter and explore the rings, the moon's atmosphere of Jupiter. So how did Galileo describe motion? Galileo described motion as a force was needed to put something into motion, not to keep it in motion. So Greeks, an object is needing to have forces constantly applied to keep it moving. Galileo said you only need to apply a force and an object will keep on moving. Letter D. What is the reluctance of an object to change its motion? Oh, here's where we have to have a moment of science. So back in the day when we had substitutes, the TV and VCR cart would roll in. Now it's just projected from internet onto the screen for you. But it's usually a cause for celebration for a Bill Nye video. For example, go ahead and sing along.
Science rules. Inertia is a property of matter. T minus 7 seconds.
Ah, everybody's favorite, apparently. I, in another lifetime, long time ago, had the opportunity to meet Bill Nye. It was a great opportunity. Bill Nye has done great things for science. The one thing us physics teachers wish we could go back in time and fix would be people understanding that inertia is a property of matter. The definition of inertia is not a property of matter. There are many, 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 many properties of matter. Melting point is a property of matter. Density is a property of matter. Volume is a property of matter. Color is a property of matter. Length is a property of matter. You could go on and on and on. There are hundreds of properties of matter. And inertia happens to be a property of matter. It's not the definition of a property of matter. On your page there, what is the reluctance of an object to change its motion? That's inertia. It is a property of matter that is reluctant to change its state of matter. So inertia, the reluctance of an object to change its motion. There was another show in the era of this educational science TV for you. It was a companion type of a show, very similar to Bill Nye, the science guy, and that was Beakman's World. And here's a little ditty to get stuck in your head at 2, 3 in the morning and poison you with the world of inertia. Let the jingle begin.
But did you know he explained much, much more than good old gravity? He said that things in motion will keep moving until they stop, and things at rest will stay at rest until they're soundly walked. Inertia, inertia makes you want to stay in bed. You gotta move your mass or you'll miss your class, so get yourself in motion instead. His first law of motion is why we're here today. Inertia keeps you sitting still or keeps you on your way. Inertia, inertia makes you want to dance all night, but there's no doubt you'll soon wear out, so slow it down. Sir Isaac was right.
And you love it. Inertia, yes, thank you, Bill. It is a property of matter. And a little more detailed look at this particular property of a matter of inertia. Here is the Canadian educational science show, Eureka.
Physics is about movement, how things move and why things move. Here is a very large thing. What do you notice about it? It's not moving. Go ahead and try and move it. You can't. It doesn't want to move. Is that because it's so large? Try and move a smaller thing then. Well, you managed to move that a little way, but it was a great effort. It was as if it still didn't want to move. Even tiny things are reluctant to move. Even a pebble takes some effort to shift. This is the first rule of physics. Things like to stay where they are. Unless there is some force to push or pull it, no object in the universe will start moving of its own accord. It's as if all objects were lazy. But why is physics about movement if nothing wants to move? The answer is that there are lots of things in the universe that pull or push on objects and force them to move, whether they want to or not. You force the pebble to move. And since things are lazy, you'd expect your pebble to try and stop moving as soon as possible, wouldn't you? Well, you'd be wrong. Strangely enough, although when the pebble was at rest, it wanted to stay at rest. Now that it's moving, it wants to keep on moving. In fact, it would like to keep on moving forever and ever. The only reason it slows down and eventually stops is because things in its path force it to stop. The resistance of the air, or a tree it bumps into, the roughness of the ground. But if there were no air or rough ground or trees to get in its way, if you were in outer space, for example, when you kicked your pebble, it really would go on moving forever and ever. It would never stop. So how can we say that objects are lazy? If the pebble's moving, it's not being lazy, is it? Yes, it is. It takes just as much effort to stop moving as to start moving. You get a feeling for this when you're ice skating. When there's hardly any resistance to your movement and it's easier to keep on gliding along than to stop. The same goes for the pebble. If nothing gets in its way, if nothing helps it to stop, it will have to make all the effort to stop by itself. And it's much too lazy to do that. We can now modify the first rule of physics from things like to stay where they are to things like to keep on doing what they're already doing. If a thing is at rest, it wants to stay at rest. If it is moving, it wants to keep on moving. In other words, there is lots and lots of laziness in the universe. Physicists have a special word for laziness. It comes from Latin. Inertia.
And to round off the autograph picture collection here, we have a picture with Ernie McFarland, the creator of the Eureka series. Letter E. What is mass a measure of? Well, this is where you're going to get very sophisticated in your science careers and sound extremely smarticle. Thus far in your science lives, you're probably considering mass as stuff, or more specifically, the amount of matter an object has, the measure of the amount of matter. Well, in the world of physics, we're going to give you a much more formal definition, and mass is a measure of inertia. So when you're measuring inertia, you're measuring mass. The SI unit of mass is the kilogram. Now, you wouldn't necessarily say the SI unit of inertia is the kilogram. It's more by definition, mass is inertia. So with letter F, describe the following motion in terms of Galilean dynamics. Dynamics, what causes motion? Galilean, meaning you can ignore the effects of friction in the sense that if you apply a force on an object, it will continue in motion. So in terms of Galilean dynamics, the tableware, it's just sitting there. It wants to keep on sitting there, and it does. The tablecloth, it's just sitting there. It will keep on sitting there until you set it in motion. And once the tablecloth is in motion, it keeps on moving. And the reason we say to pull downward is so that if you were to pull upward, you don't impart that upward force on the objects. You pull down. Another thing before you go and get your family's best china and set it up and show off your science skills with the family is to make sure if there is a hem along the edge of the table linen, make sure that that is the part you're holding on to. You don't want to pull nice and smoothly and then at the very end a tiny hem imparts an upward force, disrupting things and maybe causing crashes. So describe the following motion in terms of Galilean dynamics. The tableware is just sitting there. It wants to keep on sitting there. So because of the tableware's inertia, it keeps on sitting there. And this is a moment of science that was forgotten in a movie, How the Grinch Stole Christmas. But the actor Jim Carrey decided to go ahead and give the effect that they were after once we realized that, hey, inertia is a thing. It's a property of matter. Inertia. There we go. That's what they were after. Just forgot their physics for a moment. Next we have a former student of mine, students of mine who created this little human, and they have shared with him insight into world of physics.
Because
Of
Sir Isaac Newton. What do we know?
And it stays up top and it stays.
Yeah. If we push the bus, what happens?
It falls down.
Yeah. Where does the bus go?
In here.
Inertia, that car sitting on top, continues to stay at the top, similar to the pin drop that you did in carnival days. Similar to this, where the likely explanation, the truck came to a stop, but the roofing material probably not strapped in securely enough. Maybe it was just resting on the top, but it was moving. It was moving with the truck. The truck came to a stop, but the roofing did not, and continued forward. Another example of inertia here. It's not the invisible football player. The football player is here, so the camera has just caught the instant where the player was moving forward and continued to move forward, but the helmet was sitting on the head, just sitting there, and just wants to keep on sitting there. And it does until the next second frame would show the helmet starting to fall. And the ultimate game of inertia, Jenga. Those blocks are sitting there. They want to keep on sitting there. And they do. Check out his buddy's face right there. So the stack is sitting there, wants to keep on sitting there. And much to his surprise, it does stay there. Inertia. Letter G is like the Life on the Edge carnival days. The figure to the right shows a top view of a rock being whirled clockwise at the end of a string. If the string breaks, the path of the rock is A, B, C, D, E, or a path not shown. Support your choice as though you were teaching someone who holds to Aristotelian dynamics, meaning a force needs to keep being applied for something to keep being in motion. I'll give you some time to answer that. That being, this is you, bird's eye view, top of your head. You're swinging a pebble around and around and around and around. If that string were to break, which path would this pebble travel in? And then E is for another path not shown. In the How Lazy Can You Be Part 2 segment, we'll look at which path this pebble will indeed take. So we will return to this question, but in the Part 2.